we said that the kinetic energy is proportional to the temperature. It goes the same direction. So that's Chem 2A stuff, right? Temperature relates to average motion, to movement. Okay? As long as kinetic energy goes down, the temperature will go down. Right? 2A stuff. That's from 2A. Okay, let's see the other problem on here. That's kind of definitions. Thermal energy of a system. What is thermal energy? What is nuclear energy? Chemical energy, all kinds of different types of energy, right? And they all relate to a change. In this case, when we say that a reaction is taking place, right? What kind of energies are the changes? Because in thermal energy, right, it's kinetic and potential together for every particle that is made up, that makes up the chemical system, correct? Everything, soup, right? So in this case, we have different definitions of different types of energies, like each of these statements refers to a different type of energy. Chemical energy, thermal energy, nuclear energy, and so on and so forth. So what will be the answer here? Thermal energy, it goes with temperature of the system, right? When the temperature changes, that means that part of the system, energy of the system that changes, we call it thermal energy. And then we have also other things that you can see from here. Let's go number 9. It's pretty interesting. Water is boiling in 2 pots. One is covered and the other one is not covered. And you are ready to make tea. So you leave the house, you turn on the stove and go. If everything else is the same, except one is covered, the other one is not covered. When you come back, you find the pot which is no cover, doesn't have any cover, but it's cooler than the one that is covered. And here is different statements saying why. So we should pick up the correct answer on here. It's a good problem because we really understand how these things work at the molecular level, okay? So what do you think is the answer? How many people say A? Let's see your hands. A. A, B, C, D, E. Okay, so you already know. Have you done this practice? Yeah? Where did you do it? Oh, they are very, oh, that's good. So you understand why this is happening, right? We have a speed distribution, right, for everything. Could be solid, liquid, gas, really there's a distribution of speed, right? So when something gets cooler, it's because the molecules that have the highest speeds, they're jumping out and they leave. You still have different speeds, but now because the molecules with the higher speeds are gone, the average speed is lower, and that means the temperature is going to be lower. That's pretty cool, right? Okay. So let's do some problems now. Are you ready to do some problems? Let's do this one here. Pretty easy, actually. You just have to be careful with the signs. We talked about the signs. You really don't need to be too afraid of it, right? It's not a big deal. You should do it right. So we have, in this case, We have a reaction, that's a combustion, right? We burn actually propane with oxygen, CO2 and water. For that reaction, we have delta H minus whatever, 10 kilojoules. You need to be really careful with the units because the problem could give it to you on purpose in kilojoules and joules, and if you don't notice it, you might get the wrong answer. Usually they are pretty close to them. The work that is performed usually is small, very small. And that's why later we'll see when we do thermodynamics. Actually, when we do for chemistry, many times you take delta G. We're going to talk about it later. Actually, we don't need to talk about it now. But it's good to keep it in mind that the work that is done by these systems when you melt ice or water freezes or chemical systems, the work is actually most of the time almost zero, and compared to delta H to delta U. So you can see now here that's about the same. Well, that will tell us that actually the work is going to be really small. You can predict it now. Okay, so here's a chemical reaction. You can see the combustion, right, of propane. Then we have the enthalpy of the reaction is minus 2042 kilojoules, and the change of internal energy is also minus, reduced. So we're going to find out how much work is done, right? So that's first the equation of first thermodynamics. We can start from the definition of enthalpy, right? Or you can just remember the equation. Either way. It's good to remember to derive such equations, right? Not just memorize everything and look at the back of the page, right? So you can start from enthalpy, which is equal to U plus PV, right? And for this class, we consider external pressure to be constant, right? Be external constant, otherwise we need to use differential equations. This is not the class to do. Okay, so we have these things, we have this equation, we have delta H delta U, so you take the change. Delta H is going to be equal to delta U plus P external delta V. Right? Where's the work? Well, here's the work, right? Now remember, when you have work, the way we need to have it, so we'll be consistent with our definitions about what happens to the energy of the system in chemistry, speaking in chemical terms, to be consistent with the definition about delta. Yes, delta is a mathematical definition. When we ever say delta of something, we mean final minus initial, right? The value of final and the value of whatever it is, initial, right? It's always delta V is equal to V final minus V initial, right? That's mathematics. And we want to be compatible now with the definition we give about energy, right? When energy goes into the system, delta U becomes positive, or delta H becomes positive, yes? So to be consistent, we have to define the work as minus P external delta V, okay? Mathematics tells you the work is Px delta V, that's it. But if you want to be consistent with the terminology we use for what happens to the energy of the system, chemically speaking now in this class, we need to put that minus there to be consistent. Remember that? That's why we do it. So if we do that, then from these two there, we're going to have delta H is equal to delta U. This delta V is going to be minus W. Okay, so if we want the work goes the other way, it will be delta U minus delta H. So now you have the equation really ready to use. You put exactly what you have, you don't change anything. Minus delta U minus 2044 kilojoules minus, right? Minus, maybe I should not put it there so there won't be confusion. Minus delta H in parentheses, delta H minus 20, 43. You don't need parentheses, you will probably make a mistake. You'll probably get it wrong. Okay, so that will give you minus 2 kilojoules. Minus 2 kilojoules. So you have to be careful, consistent. Whenever you are very, to have signs correctly, it's important. Whenever you work with signs, it's very important, like in this case, always use parentheses, right? Otherwise, it's a multiple choice problem, you might know how to solve it, and you make that mistake, you lose the whole point. Then it's not fair, it's not good, right? But I didn't make that educational system to circle numbers to proceed to the next thing. Do you know there are schools that you can go up to 12, 8 grade or something, and they don't have any grading? There's no any grades? You know that? There are schools like that? There are schools like that. You can finish elementary school 6 years, you can go another 4 years or whatever. You go from one class to the other, no grades. They're called schools full of creativity. There's things like that in the world, you know that? Why don't all schools to be like that? Why not? Huh? Why do I have to circle ABCDs? Think about it. Okay, and then you have all these strengths that you have. We're going to try to reduce it after a few minutes, right? We'll make an effort to reduce it, right? Yes? Don't smile. Can you give me 5? Yeah? Yeah? Can you give me 5? I don't see it. All right. Okay, let's go to the next one, 13. So we still things about vapor pressure, so that reminds us which law?